All right, well, good afternoon, everyone, and welcome to our first sound learning session of 2021. And all of our sessions this season will be hosted through Zoom webinar. So thank you for joining us today. There may be still a few attendees who will join us in the next few minutes. Currently, we have 18 on the call, and I believe the registration had about 28 or 27 on the list. So hopefully a few more people can join us. The presentation today will be given by Mr. Ken Selger, and the topic is black holes. Just a little bit of housekeeping before we get started. So Mr. Selger will go through his slideshow presentation, and everyone is going to be on mute throughout the presentation. And once Mr. Selger has completed his presentation, there will be a Q&A session, an opportunity to ask Mr. Selger a question. So in your webinar controls, where you have your microphone and your webcam, you should also have an icon that looks like a hand, and that will give you the opportunity to, if you click that, it will notify me as the coordinator that you have raised your hand and that you wish to ask a question, and then we'll go one by one based on the order of hands that have been raised. Once that happens, I will have to ask to unmute you. So you may have to, you'll be prompted to unmute yourself, and that will allow you to talk. And then we'll go on to the next question. Following the Q&A session, there's going to be a brief poll, which is the typical sound learning session survey. And it will be very brief. There's 4 or 5 questions and should take less than a minute to complete it. So please stick around after the Q&A to fill out the sound learning session evaluation or poll. And with that, I will kick it off to Mr. Selger.
Thank you, Travis. Appreciate the intro. Welcome to black holes. I hope everyone enjoys the topic. So let me tell you what we're going to be doing. Black holes is a star. So what we need to know is all about stars, but not all the stars are the same. So black hole starts as a star, and we need to learn how stars are born, the characteristics of stars, and the life of a star, and the life after death of a star. So who am I? I'm a person with a BS in physics. So I'm not sure everyone saw the last slide, so we'll go over it again quickly. It's all about stars. Not all the stars are the same. A black hole starts as a star, and we have to learn how a star is born, the characteristics of a star, the life of a star, and the life after death of the star. So who am I? I have a degree in physics, and I've taken some classes at FGCU in astronomy, oceanography, geology, and climate change. And I worked on the Hubble telescope. I was on the design team there, and I was the chief engineer of the Fine Guidance System, which was a part of the Hubble. The other thing which is germane is that I was the program manager of the STAR sensor, which is currently up on the International Space Station. So what did I do? I was an engineering physicist. My first job was in measurement standards while we were building the Atlas rocket, which you see here on the right. We certified measurement instruments up to 1/1000th of an inch. Down in the lower picture are some typical optical flats that are being examined, and you can actually measure deviations from a perfect plane up to 1/1000th of an inch. So what is a black hole? Black hole is the remnants of a star whose gravity has increased so much that nothing can escape, not even light. It's very, very compact, very, very dense. It has collapsed from something that was millions of miles across to only a few miles in diameter. There, it's generally believed there are millions of black holes in the universe, but there could be billions. There's also a wide belief that in the center of every galaxy is a black hole, but they all begin as a star. So how do we know they even exist? Well, this is an artist's concept showing what happens when a galaxy passes by a black hole. You're looking at the edge view of a galaxy. And this, you'll repeat here, the center part is where all the stars are mostly are, but the arms stick out on either side. And you can see the distortion that takes place when it goes by a black hole. So to get an appreciation of what the scale of things are, I have this little video which I'm going to show. We're now zooming out of Google headquarters. And now we go back. And a smiling young lady is still there. And now we go and visit her up close. So they're talking about the emptiness of the atomic space, and we're going to bring that up again in a few slides. And now we're back to normal. So the strange objects that we found in the sky was actually predicted by Einstein's general theory of relativity back in 1915. He didn't realize it at the time, but that will come out with others that will use that general theory of relativity to predict these objects. We found some of those objects as we got bigger and better telescopes. During the Manhattan Project, the work that we did there in understanding the physics of the atomic bomb helped us understand how these objects in space actually function. So we shall explore these new objects in this session. So the first place we want to go is to what we call the stellar nursery or nebula. The picture on the right is called the pillars of creation. In these clouds of dust and molecules, they are where they believe many of the stars are actually born. The one on the left is another example. Both of these pictures are from the Hubble telescope. The classic little W dark spot on the right corner of the right picture is what they call the WFPIC, the wide field planetary camera takes that picture and has that signature. So anyhow, how a star is born. These gas molecules, clouds collapse. And they're not sure exactly why. Some people have speculated that it's the shock wave from a supernova that actually starts the collapsing. I sort of like the idea that static electricity may play a part in pulling these things together. So what happens is the atoms and molecules collide, and when they do, some of them adhere to one another, creating more mass, more gravity, and at the same time generating heat. Realizing that this collision has energy, and the energy is absorbed and comes out as heat. So gravity keeps pulling the atoms and molecules inward, while heat pushes them outward, creating a ball shape. This heat keeps building and building, and as the heat gets up to 1,000,000 degrees, colliding atoms fuse together, creating a nuclear reaction. This is an H-bomb or hydrogen fusion. So astronomers, for ever since they started looking at stars back in the 1600s, have been trying to chart the stars and try to find some pattern about the stars and understand what their origins are. And what they did here is they have charted the illumination on one side and the color of the star on the other. I'm sure many of you have seen stars that have a little bluish tint to them or a little reddish tint. So those are the colors that they're looking at. And they calculate what the luminosity is for each of these stars. And they plotted them up on a graph paper, as you see on the right. And the emerging pattern is called the main sequence. Stars form along this curve and stay there their whole life, all the way along this area here. There's some stars that are up in this area, which are at the end of life, as well as these down here are also at the end of life. But during the main life, this is the main sequence. And our sun is in this general center area of the chart. This chart I like particularly because it shows the entire evolution of a star, from its birth here on the right, as the first fusion takes place, and the debris gets cleared out. This star forms and is very, very, very stable as it goes through time. And time is moving around us in an arc. And you can see that the star changes very, very little until near the end of its life. And then suddenly starts to become much, much larger, and it's called a red giant. And then eventually gets to this very huge, large solar mass, which then implodes, and you wind up with what we call the planetary nebula. And eventually, the debris that's been left from the implosion falls away, leaving a white dwarf, which is not quite shown on this map. So But it all depends upon size. Large stars burn fast and have short lives. Some will explode as a supernova, and the remnants will be scattered in space to become parts of another new star. Small proto-stars never go nuclear and become space debris, and they too would become parts of new stars moving out. Mid-sized stars like our sun are very, very stable and burn for billions of years. Our sun is halfway through a 10 billion year life. So we got another 5 billion years to see it go away. So the black hole theory, as I said, came about from Einstein's equations for general relativity, and Schwarzschild in 1916, the following year, was able to solve those equations and showed that a black hole was possible. He believed it was a mathematical quirk, that black holes really did not exist. The math would just suddenly blow up and you'd find things like you were dividing through by 0, which gives you infinity, and things that just mathematically didn't make sense. But it's only in the last 30 years or so that astronomers began to really think that, hey, black holes are probably out there. So here is the sequence of the kinds of stars that are formed. On the top part, we have the low to medium sized star. It comes out of the nebula, goes into the main sequence, eventually as it nears the end of its life, becomes a red giant. It then implodes and you have the planetary nebula, and eventually the nebula falls away, leaving the core, which is a white dwarf. But on the high mass side, if it's a really big star, it goes in through the main sequence in a much quicker time, comes out as a red giant, and then goes into a supernova where it implodes again. And this time, there are two paths, depending upon the mass. One path will take it to become a neutron star, which we'll talk about shortly. And then if it's a really big star, this is the one that will eventually become a black hole. So how do we know about these stars? Well, as we made bigger and better telescopes, we were able to see how stars evolved. For example, using Mount Wilson 100-inch, Edwin Hubble found that there were galaxies. They didn't know galaxies existed until Edwin Hubble's discovery in about 1925. He found things that were floating around up in space. And when he got his hands on the 100-inch, he realized those were galaxies. And they had thought that the Milky Way was the only thing out there, that everything was in the Milky Way galaxies. When the Mount Palomar 200-inch telescope came online, they were able to discover dwarf planets like Eris. NASA, in the 1970s, decided to put telescopes in space so it could see the stars without the atmosphere blocking some of our view. So what did NASA do? NASA created what they called the Great Observatories, 4 significant telescopes covering different portions of the electromagnetic spectrum. On the left, we have the Compton Gamma Ray Observatory, followed by the Chandra X-ray telescope, and the one I worked on, the Hubble Space Telescope, and then finally the Space Infrared Telescope Facility in the IR. So showing this on a little different kind of a graph to show you where they fit into the electromagnetic spectrum, we have the infrared telescope is the first one I've listed. And then on the top bar, you can see how much of the atmosphere lets you see through it. Only in the visible section of these telescopes is there a clear view. Most of it is blocked by the atmosphere. The atmosphere doesn't let those radiations through, and that's why they want above the atmosphere to see be able to observe the stars. So what they find, they found a whole bunch of different objects, and I'm going to list them here. But they were planetary nebular clusters, novas, supernovas, pulsars, neutrons, and black holes. So we're going to go through each one of these quickly. A planetary nebula, which was probably a poor name choice, because when it was first found, they thought they were planets. But it wasn't until the better telescopes came along, they found that they were not planets. It was about 70 years ago, they solved the mystery with nuclear physics on what these things really were. And it was the end of life for a normal star. So the planetary nebula are actually some of the most spectacular images to see. I've got several of them here, and I'm going to point out a few things that are apparent. Remember, these are stars that were giant red stars, and they imploded. And apparently they do it in a multiple of times. In other words, it's not just one implosion, it's multiples. And we don't understand why that is. The one on the right here, you can see different rings where there are different implosions or explosions. So it really is clear in the image here on the left, where you can see that there were multiple rings of debris that were thrown out when this particular star imploded. And they have a variety of shapes, and the colors are spectacular. Again, more planetary nebula, and they have, as I see, a relatively different looking, no matter, depending upon which one you look at. So the next thing they found was there were clusters. They found stars that were grouped together, which they called clusters. Pleiades is probably the most famous. It's also called the Seven Sisters. There are 7 stars. What they believe happens is that that it starts with a very, very large molecule cloud, which breaks into multiple clouds, with each forming a star. So you might have a cloud that breaks into quarters, and all 4 pieces will become stars. So the stars in each cluster are about the same size and age. They don't understand why that happens, but that's what they believe is going on. Nova. This is when 2 stars interact, and you suddenly notice that one of the stars becomes extremely bright. And the reason is one star is transferring matter to another. Now, you may not realize it, but most stars in the universe are binaries, 2-star systems. They form very commonly, 85% of the stars they believe are 2-star or binary star systems. We almost had one in our solar system, with Jupiter almost becoming the 2nd star in our system, but it never quite made it. Supernovas. Supernova gets its name because it's 1,000,000 times brighter than a nova. So it really gets noticed. There aren't very many of them, or very frequent, but they do produce a lot of energy. And what's going on in this star is all the stars start with hydrogen that fuses together and produces helium. Well, if it's a big enough star, the helium will fuse with itself and the hydrogen to produce carbon. And then carbon will fuse and will produce neon. And then finally oxygen, and silicon, and finally iron. The heavier, so all the most common elements that we know of on Earth came about this way. This is how they were formed. The heavier elements that are on the periodic table were formed by a supernova explosion when the higher energies are available to even create more elements in our periodic table. Then there are two other stars which are related, excuse me, pulsars and neutron stars. Neutron stars rapidly capture neutrons, creating heavy elements. They expel huge masses of charged particles in jets about an axis. There are axes that they're spinning in. These jets are throwing these charges out, and accelerating charges create X-rays, and we can see them from their X-ray signatures. The rapidly rotating ones become pulsars. Excuse me. They are like a lighthouse. When you see the lighthouse as the beam sweeps by you, the same thing happens with a pulsar. It can only be seen when the pulsar beam is pointing towards us. The star's rotation sends a regular X-ray signal. You see a blinking signal or a blinking X-ray. And when it was first discovered, there was a lot of speculation. It was aliens trying to contact us. Turned out, nope, just some stars. So let's go and take a look, listen to what a pulsar is from NASA.
A pulsar is a rapidly spinning neutron star, which is the small, incredibly dense remnant of a much more massive star. A teaspoon of matter from a neutron star weighs as much as Mount Everest, and a neutron star is so compact that a ball about 15 miles across contains more matter than our sun. Neutron stars spin between 7 and 40,000 times a minute and form with incredibly strong magnetic fields. Rapid spin and intense magnetic fields drive powerful beams of electromagnetic radiation, including gamma rays. As the pulsar rotates, these beams sweep the sky like a lighthouse. To a distant observer, the pulsar appears to blink on and off. Pulsars slow down as they age, but some of the oldest pulsars spin hundreds of times a second. Each of these millisecond pulsars orbits a normal star. Over time, the impact of gas pulled from the normal star has spun the pulsar up to incredible speeds. This accretion may be the cause of their weaker magnetic fields. Despite this, these pulsars also emit gamma rays.
Okay, moving on. Yep. So, many of these strange objects emit X-rays, but how can you capture an X-ray image? X-rays pass through most objects. So what kind of a lens do you need to focus an X-ray? Well, the Chandra X-ray telescope uses concentric nested mirrors, which are parabolic and hyperbolic, to focus the rays down. How does it do that? Well, the rays reflect at the shallow angle of incidence like a mirage off the pavement on a hot day. The reflecting surfaces are parabolic and hyperbolic to produce a classic telescope design called a Cassegrain. The work was made by some of the same engineers and scientists who worked with me on the Hubble. So that's a plug for the company that I worked for, which was PerkinElmer, that made the X-ray telescope, the Chandra X-ray telescope, as well as it made the IR telescope. Like the Hubble, it is still functioning today, years after it was designed end of life. So it's still functioning. Nobody has a guess as to how long it's going to keep on functioning, just like the Hubble. So anyhow, going to the black holes, where where the black holes have these very large stars, but they use up all of their fuel and stop producing heat. Without heat pushing outward, gravity pulls matter together. It crushes the atomic structure, stripping electrons and increasing density yet again. The increased density increases gravity, which pulls matter even tighter in a runaway process. Soon, nothing can escape. The result is an incredibly dense ball of matter, all molecular and atomic motion stops. No residual energy remains. Without residual energy, temperatures drop to almost absolute zero, which is minus 459 degrees Fahrenheit. So a black hole gets born. There's an area near the black hole where nothing can escape and is pulled back into the black hole. That area is called the event horizon. So Einstein's theory predicted black holes, even though Einstein didn't realize it at the time. But the equation breaks down when applied to black holes. The equations predict infinite density, which can't be, and an absolute zero temperature, which is another impossible thing. It is thought that some other theory will come along one of these days to describe what happens mathematically for a black hole. So there was more to this presentation, but it got too close to the black hole and was sucked in. So that's the end of the presentation. I guess we're ready for a Q&A. Do we have any questions that anybody would like to ask?
Mike McDowell has a question.
And what is the new James Webb Telescope going to produce that will be different from and more, and I guess better than the Hubble? What will we learn from that telescope?
Okay.
And why is it different?
Good question, Mike. The James Webb Telescope to be launched now, I think it's October 30th of this year in South America, near the equator, where it will get a boost from the Earth's rotation. It is 10 times larger in diameter than the Hubble. So we have a 2.4 meter telescope for the Hubble, and this will be, I think it's 25 meters across. So it's a good size, and resolution is directly dependent upon the diameter of the telescope. The bigger the telescope, the finer the resolution, the finer the detail can be observed. It's going into a solar orbit located approximately 1 million miles from the Earth, going around the sun just like the Earth. I don't know whether it's considered leading the Earth or following the Earth, one of the two. It's in a special spot in the orbit where it needs minimum upkeeping as far as attitude controls. There's a balance point where the amount of forces on it are at a minimum due to the other planets and due to the sun. So there's less station keeping than would be required in another spot. Now it's an infrared telescope, so it's replacing the CERTA telescope and going to be looking mostly in the infrared spectrum, which is where they can see more of the creation of stars that are in the stellar nurseries. Does that take care of it, Mike?
Yep, thank you.
You're welcome. Anyone else?
And I believe Mary Ann Ogg might have a question as well. I'm going to allow her to talk and unmute her.
Am I unmuted?
Yes.
Oh, hello. Hey, Ken, that was a spectacular presentation. Thank you.
Thank you.
Oh, if the black hole is dead, I mean, the star has collapsed within on itself. What becomes of anything that gets sucked into it?
Well, that's a good question. They're not sure. They believe that it will actually get crushed from the gravity and literally just made part of this incredibly dense structure that it is. But there's a number of speculations I've heard about where they discuss, what happens if you fall into a black hole.
Yeah.
I'm not sure that they're really germane, but they do, crush everything that's coming in because the gravity is just huge.
So it's gravity that's.
Gravity is still there, right?
As an aside, do you remember that hilarious movie where some space cadets go into a black hole and climb out the other end?
I don't recall that one. I'm sorry.
You missed it. One other, just as an aside, kind of as an English major, who named the event Horizon? Because, that sounds like something that an event's going to happen, and it's like the end of all events, isn't it?
Well, it's the edge where the events happen or when they go in. I don't recall whether it was Schwarzschild. I might have been Schwarzschild who coined that phrase. But it's at the edge, and what happens is with certain charged particles, they get pulled in at that spot, and that's when they release X-rays, and the X-rays can be detected. So
okay.
they see the X-rays from the charged particles being pulled in.
So it's kind of the horizon of an event from our point of view.
Yes.
The event being the visualness of the X-rays then.
Right.
Okay, very, very, this whole business is also fascinating. Thank you.
You're welcome.
And Miss Barbara Rosenblum has a question.
Sure.
And Barbara, you'll just have to unmute yourself by clicking the icon of the microphone.
Okay. Thank you. Can you discuss the point that nothing in the universe can disappear?
I have trouble understanding you. So echo on it.
Sorry. Okay, I'll try again. Can you hear me now?
Much better.
Okay. Can you discuss the point that nothing in the universe can disappear?
Whether there's any matter that's created or destroyed, is that what
Right.
you're referring to? Yes. That's again, obviously a speculation issue. They think all matter is here and nothing is being destroyed. And there's speculation of whether the universe will keep expanding or come back and stop at some point because it's expanding now and then become steady at that point, or will it all collapse again into a single point? So it's that is one of the topics that physicists talk about today, and there is no solution, no answer as to what the right answer is. It's just speculation as to how that would happen.
Okay, I have another question.
Sure.
One is, have you read The Three-Body Problem by Shan Liu?
If I have, it's been a long time.
Okay, so basically the universe, though, is just a very perfect recycler.
Yes.
Okay.
Yes, absolutely. As you know, these stars that do reach the end of their life and implode, they leave debris, and that debris is floating around, and it becomes the parts of new stars that form. So
Mhm.
it's a recycle. It's the best recycling we've ever found.
Right. Thank you. That was a fun presentation. Thanks.
Good. Thank you.
And just in case anybody joined us late, if you do have a question in your webinar controls, there should be an icon of a hand. If you click that, you can then raise your hand, and it will identify that you have a question, and I can allow you to speak. Okay, Mr. Roger Levine has a question. And Roger, if you'll just unmute your mic, you'll be all set.
Thank you, Ken. Good presentation. Hey,
Thank
do you
you,
have
Rob.
any idea how many black stars have been reasonably well identified?
Well, as I alluded to in the presentation, they're very hard to find, obviously, and only can you find them by what happens by something passing in front of them.
Understood.
And there's speculation that in each and every galaxy, the center of the galaxy is a black hole. It would make some sense from the standpoint that when they calculate the mass of the galaxy and the stars that are circulating around the galaxy, there's some missing mass. Now, it's been called dark matter, but some of it may be, or maybe all of it may be a black hole in the center of the galaxy, creating the gravity that they can see generating the orbits of the stars that are in that galaxy. Because right now, when they do the calculations, there isn't enough matter being available to create the star motions that they can actually see. So it may be that every single galaxy has a black hole. And the last count I saw, anybody even speculating how many galaxies there were hundreds of billions of galaxies. So you can take it from there with how many there are.
Second question, Ken.
Yeah.
Are these eventually, in some point in time, going to be potholes towards, as far as space travel is concerned?
Say again?
Are these potential potholes with regard to space travel?
Potholes. That's an interesting comment. I don't know. I don't think so. The reason being that if the speculation is correct that there is a black hole in every galaxy, it just becomes a very simple calculation as to its effect on space travel. And of course, you're dealing in motions or distances that are huge. So I'm not sure from a human standpoint, it makes much sense. But it from, looking at things that are flying around out there, yeah, you can calculate it and determine what the effects would be. And you don't even need anything special, just Newton's equations are fine to calculate that information.
Okay, thank you.
Mr. McDowell, did you have another question?
You mentioned, Ken, that Jupiter might have been a star. What in its makeup or what occurred so that it became a planet, admittedly an immense one, but what would have been different? How could it become a star?
Good question, Mike. It apparently developed late in the forming of the solar system. If it had formed earlier, it might have gathered up enough fuel, hydrogen, and had enough heat to start a nuclear reaction. So that's the speculation that was our closest thing to a second star. But as I point out, most stars have two, but they're not one, they're two. They're binaries. 85% are binaries. So it happens a lot, more often than not.
Any other questions for Mr. Selger? If there are none, then I'm going to go ahead and launch the poll. You should see that appear on your screen. Again, there's about 5 or 7 questions there. If you would please take a moment and complete that poll, and that will provide some valuable feedback on the Zoom webinar presentation, how it went today, and how we can improve in the future. So we appreciate you attending today, and we hope you enjoyed Mr. Selger's Black Holes presentation, and we look forward to seeing you at the next Zoom Sound Learning webinar.